Last time I sort of left off in the middle of discussing this sort of most simplest example of a topological phase. So let me finish up that discussion. So remember last time I introduced a sort of criterion for, written in terms of density matrices that can be useful for distinguishing between topological phases and trivial phases. So I'm going to flesh out the toric code example and see how that's an example of this non-trivial criterion. So remember what the toric code was. So this was a lattice model. It was a lattice model in 2D. I had spin 1/2 living on the links of a square lattice. I had a Hamiltonian, which was made out of two kinds of terms. So remember, we had this Hamiltonian, and it was made out of these two kinds of terms. So the first term was a sum over all vertices V. Say this was the vertex V. And it was the product of Pauli sigma x operators around the links around that vertex. And the second term is a sum over plaquettes P, so it's sort of a dual kind of term. And it's a product of sigma z operators around the links of the plaquette. And so last time I argued that these terms are all mutually commuting, right? So the A's commute with each other just because they're all built out of Pauli sigma x matrices, and all sigma x matrices commute. Similarly, the B's commute with each other. And then I argued that the A's and B's, any A commutes with any B as well, because despite the fact that these are built out of sigma x's and these are built out of sigma z's, so naively you might think of this as anti-commutation. When you look at an overlap between any vertex term and any plaquette term, it always happens on an even number of links. So that minus sign always appears to an even power. So it turns out to be a plus sign and returns to So these are commuting terms. So there's a common eigenbasis for all these terms and the Hamiltonian which is built out of them. And so to find the ground state, it's sufficient to simply find the highest eigenvalue, eigenstate of all these A's and B's. Okay? And that's pretty simple because these A's, Pauli matrices all squared plus 1, so Pauli matrices have eigenvalues plus or minus 1. This is built as a product of this term of Pauli matrices. So this term it only has eigenvalues plus or minus 1. So all we really need to do is just find a state or states which are eigenvalue plus 1 eigenstates of all the A's and all the B's. If we do that, we're done. That is definitely the ground state because there's nothing that can possibly have lower energy. Just from this, the lowest energy you can get is just making all these plus 1. So, okay, so what does that state look like? So there's a nice pictorial representation of states in this model. This model really lends itself to sort of visual explanation, even though it's defined on a lattice. You can really kind of think about it in some coarse-grained way, as we'll see in terms of the loop gas, and to be able to do it, to think about this in a visual way, I'm going to think about I'm going to think about each link as either being occupied or not occupied, according to whether it's a sigma x equals plus 1 or minus 1 eigenstate of, according to whether it's a plus 1 or minus 1 eigenstate of the sigma x operator. So each link has an associated operator, and I can think of it as being empty or occupied. This sort of chooses a basis to work in. You can certainly work in other bases, but this basis makes it sort of makes everything very transparent. So the definition is that if I look at the sigma operator on a given link L, I act on a state of psi. So psi for now just describes the state of a single link, so it's just a qubit. I'm going to think about eigenstates of sigma x. They're either +1 eigenstates or -1 eigenstates. In this case, I say that the link is, so if the +1 eigenstate will be, link is empty, and -1 will be occupied. Okay? So then any configuration on the entire lattice, in terms of the sigma x basis, if I think of a configuration of spins on these links, which is on each link an eigenstate of sigma x, there's a corresponding picture that's associated to it, which is just a set of all occupied links. Okay? Right. Okay, so now working, again, continuing to work in this eigenbasis of sigma x, let me try to diagonalize these a's and these b's. Mike, do you have a question, or are you just okay? You had a question, I'd be very okay, so I'm going to sort of, using this visual description, I'm going to construct the ground state. Something that's a +1 eigenstate of all the a's and all the b's. So basically, I'm just demanding that I have a +1 eigenstate of all the a's and all the b's. So let me start with the a's, the a operators. Those are easy, right? Because those are written in terms of the sigma x basis. So when working in terms of the sigma x basis, it's going to be easy to diagonalize that. Any configuration, sigma, in the sigma x basis is an eigenstate of that term. And what this term really says, if I want to, I want to find the lowest energy state. I want to find the ground state. So because of this minus sign, I want the +1 eigenstate of the A. So I want to impose AV equal +1 as a constraint. Okay. So now, if you look at what AV does, is it multiplies the sigma x's on all 4 links surrounding B. Okay. So I get a +1 every time I have an empty link, and I have a -1 every time I get an occupied link. And what I want to do is I want to impose that the product of all 4 of these plus or minus signs is equal to +1. In other words, I have an even number of occupied links adjoining each vertex B. Okay, so so imposing this at a given vertex B basically gives an energy penalty. Well, if I impose this as a constraint at every vertex B, it basically it eliminates some configurations. Okay, those will be high energy configurations. So it eliminates those configurations from the ground state manifold. Those configurations will definitely not enter the ground state at all. Their amplitude will be 0. And what kind of configurations does it eliminate? Well, so it eliminates a bunch of configurations. What it allows for are configurations like, I don't have to pull it in Chuck, but here, I'll just do this. Okay, so for instance, this configuration is okay, right? So this is the dotted line means empty link, and the solid line means occupied link. Similarly, the all empty configuration is okay, and the all occupied configuration is okay. And then various other configurations which are other configurations where you have 2 occupied links. Those are all okay. So these are okay. What's not allowed is basically having either a single endpoint, so a single occupied link at this vertex B, or let's say 3. Okay, that's an odd number, so these are not okay. Okay, so immediately from this, we can see that if I impose this a sub b plus +1 as a constraint on every vertex B, then I've restricted myself to configurations which form loops, okay, loops without endpoints. Because I've eliminated configurations like this, right? If I had a configuration like this, then I had an endpoint of a loop, okay? But that's not allowed to appear in the ground state manifold. And similarly, this is not allowed to appear, so it's like this trivalent junction is not allowed to appear. The only thing that's allowed to appear is, things like this, which is something with no endpoints, empty things, empty vertices, and also things like this. Now you might say that this is a 4-valent vertex. That's not a loop. That's true, but I can sort of, in my head, I can sort of resolve this singularity this way. I can just sort of think of this as being composed of two disjoint loops, which is something that I can't do here. Like here, no matter how I try to splice things, I always end up with an endpoint. But here, really, I have loop configuration. So imposing the vertex term just sort of reduces your ground state manifold to be supported on loop configurations. Okay, so ground state supported on loops. Okay, now, okay, should not have started on that board because now I can't lift it. Okay, well, I guess that's just memorize all that. Okay, so
You can write in the top word.
yeah, I mean, in principle, but yeah, all you really need is this. So yeah. Okay, so that's what imposing the A terms constraints give me. Now let me, on top of that, those constraints, impose the B terms. Okay, so the B terms are just some additional constraints, and I know they commute with the A, so I can, I can sort of impose them on top of the A constraints. It's not like imposing the A, it's not like the B constraints fight with the A constraints. If they didn't commute, then I couldn't sort of impose them both as constraints. One would be fighting the other. But because they commute, it's fine. So I could just impose the A constraints first. I restrict myself to loop configurations, and then I impose the B terms. So I sort of see, what imposing the B terms gives me in terms of loop configuration. So, so the point is that there's still very many different loop configurations. Even after you've imposed all these A terms as constraints, you still have a very large manifold of allowed states. Basically, any linear combination, any superposition of loop configurations is still a low energy state, lowest energy state for the A's. But from that sort of very large degenerate Hilbert space, imposing the B's as constraints is going to pick out a unique ground state or close to some finite degeneracy of ground states that doesn't scale extensively. So what does B do? So B is not diagonal in this occupation basis, right? Because B involves sigma z, and sigma z is off diagonal if you work in terms of the sigma x basis. And what B really does, what does B do? It flips spins, right? So in particular, B sub p, if I act on, just to note it graphically, if I have some portion of my configuration that looks like this, where these guys are occupied, acting with B sub p on this plaquette P is just going to flip all the links surrounding P. So it's going to make these fields, make these occupied states empty and occupy these states. So, what I'll get is something like this. Okay. So all this is done is, if I think of this again, think of this thing in terms of loops, is this B sub p is kind of like a kinetic term for the loops. Okay, it makes the loops move. It's a hopping term for the loops. It makes the loops hop. Okay. So now your typical intuition is, if you have, let's say, if you don't have loops, but if you have particles and particles are hopping, you have a degenerate set of different positions. But say there's no potential, so they're all degenerate. If you turn on a hopping term for a particle, the lowest energy state is an equal amplitude superposition of all the position, equal amplitude superposition over all real space. It's a zero momentum plane wave. That's your intuition for a particle. And it turns out that here the intuition is similar. And so if you impose all these BP as constraints, as +1, so sort of looking at the lowest energy state in terms of the BPs, what you get is that the ground state, it's not a ground state, so the capital side, the medium-body ground state wave function, is equal to an equal amplitude superposition of the loops. Sum over loop configurations L of L. And there's a normalization factor 1 over the square root of n, where n is the number of different loop configurations, just so the state is normalized. So So that's just a normalization factor. But really what it is that the ground state is an equal amplitude superposition over all loops. Okay? That's what the ground state looks like. It's a loop gas. Good. So that's the model. Now remember, the reason I originally introduced this model is as a criterion for topological order. So the reason I introduced the model is because I had a criterion for topological order, and I'm claiming that this model is sort of the first non-trivial example which satisfies that criterion. So let me remind you what the criterion was. So the situation was as follows. So we had our two-dimensional system, gap two-dimensional system, and what I said was that the expectation, which is borne out, is that if I modify my Hamiltonian in some local region, that should not affect the state far away from the region in a gap system. Okay, because there's a correlation length and correlations fall off exponentially, and modifying the Hamiltonian here is kind of like changing boundary conditions here. That really shouldn't affect things sort of many correlation lengths away. Okay. But then I said that while that's true always for measuring correlations within some topologically trivial disk-like region, that can fail to be true if you measure correlations in a topologically non-trivial region. In particular, I introduced this geometry of an annulus. Okay. So I changed the Hamiltonian here. This was delta H1. And then for technical reasons, I also have to change it sort of at a different point as well. So it's actually a union of 2 points, but that's okay. I still have this, these 2 points are still sort of very far separated from each other and from this additional annulus that I introduce. And the claim is that in a topologically non-trivial phase, the thing that can happen is that a change of the Hamiltonian here and here might cause the density matrix in this faraway annular region to change, despite the fact that the phase is gapped. Okay? So this we can see how this happens in the toric code model. Now that we have this toric code example, and the way that this happens in the toric code model is as follows. What modifications am I going to make at point 1 and point 2? What are my delta H1 and delta H2? Well, it's very simple. What I'm going to do is do the following. I'm going to draw another copy of this picture that's going to be relevant to the toric code case. I just want to have a picture of this where I have a lattice. Lattice. And these two locations, right, delta H1 and delta H2, there are going to be some vertices. Vertex 1, E1, and vertex 2, V2. And I'm going to modify my Hamiltonian at those vertices V1 and V2, and I'm going to do that as follows. So my new Hamiltonian, my H prime, is going to be, it's going to look like H away from V1 and V2, so it's going to be, again, the sum over all vertex terms over vertices which are not V1 or V2, the usual vertex term. And then what I'm going to do is when V is equal to V1 or V2, I'm just going to flip the sign. So the sign in the original Hamiltonian was negative, now I'm going to make it positive. So plus AV1 plus AV2. And then I'm going to keep the Plaquette term as is. So the Plaquette terms don't get modified at all. Okay, I'm going to do this. Still exactly commuting. Everything's still easy to solve in this Hamiltonian. So, okay, so how do I solve this Hamiltonian? I already showed you how to solve the original Hamiltonian where there are minus signs here. I told you the ground state is a loop gas. There's a lot of bed links. Well, same idea here. So you can solve this Hamiltonian in exactly the same way. You still get a loop gas, except that at V1 and V2, you get endpoints, right? Because now the condition says that you want an odd number of occupied links at V1 and V2. Okay? So the ground state looks like kind of this soup of different loop configurations. It's this quantum superposition of all these different loop configurations together with some string of occupied links running from V1 to V2. Okay? Just some string, together with some loops on top. Okay? And so now, that's what the new ground state is. And how does it compare to the old ground state? Well, it kind of looks like the old ground state if I do measurements on topologically trivial regions. Okay, so if I just allow myself to look at a snapshot of this ground state in a disk-like region, maybe here, or maybe anywhere that doesn't involve these 2 points V1 and V2, or more precisely anywhere that sort of, yeah, I mean, if I'm looking at disk-like regions, I can just look at any disk-like region that doesn't intersect V1 or V2. Sort of the snapshot of the state in that region, or more precisely the reduced density matrix, looks exactly like that of the ground state. Now, you might object because you might say that, oh, if I choose my region to be this, then in this state I see this string that's crossing over from V1 to V2. I didn't have that in the ground state, but you did have that in the ground state because you can't really a priori tell whether if you see a string like this and you only observe a portion of it, you can't tell if it was connecting these two endpoints V1 or V2 or just was going to close itself, close in on itself and make it a closed loop configuration. So if you only sort of measure in disk-like regions away from V1 and V2, you can't tell the difference. This looks exactly like the ground state. But now, if you measure in non-disk-like regions, so if you measure in a region that that forms this annulus, and on the lattice it's simplest to draw an annulus in terms of a square. So just draw the following here, wavy line. So one lattice size, I guess, is good enough. If I look at the reduced density matrix on that annulus, now I will be able to tell a difference. Why? Because all it's very simple. All I have to do is count the number of occupied strings crossing from the inside to the outside of the annulus. Okay? And in the ground state of the original unperturbed system, it's always an even number because I only have closed loops. And if a closed loop enters this region, it certainly must exit it. But in this ground state of this Tor code model, I certainly have an odd number because I can have some number of closed loops plus the string that starts at V1 that must go to V2 and must cross exactly once. Okay, so more precisely, the operator that I can explicitly construct an operator O which measures this number of link crossings, or not, doesn't measure the number, but it just measures the parity of the number of these guys. And I can construct it as the product over all links L, which are perpendicular to the boundary of the same region. Just product over all these links. L perpendicular to the boundary of the same region A of sigma x. Okay, so if I construct this operator gives me +1 if there's an even number of strings, and -1 if there's an odd number from inside to outside. So then the expectation value of this in the original ground state, reduced density matrix on A is +1, while its expectation in the perturbed ground state is -1. So that means that rho A and rho prime A must be very different because your expectation with respect to this operator is
What if you measure with a topologically simple disk shape, but you include the site?
right. Well, then it's definitely not going to look like then you can definitely tell the difference. I mean, because you can measure the endpoint.
To tell the difference.
Yeah, I mean, you'll be able to measure the endpoint. You just do in that case, just the correlation function, just the expectation of AV1 is going to be different in the two cases. It's no longer going to look like, right. Is that?
I guess I just thought that, okay, maybe I was thinking you were going to say that these two cases you can't tell with a local measurement, but you can with this non-local.
Right, that
You
is
can
what I want to
also
say.
tell local.
That's right, you can also tell with a local measurement if you allow yourself to measure that site. But another thing I could have done is I could have just sort of stripped away the sites here and stripped away the sites here, right? And then you really can't measure, an excitation here because I've taken away those sites. So you can choose boundary conditions appropriately in such a way that you're sort of staying in the ground state manifold, and then really you can't tell the difference without. Other questions? Yes.
So that line looks a little bit arbitrary. So I think in each, maybe in each superposition, so there's a superposition of a bunch of different possibilities. So in each one, there's one line going.
Yeah,
Correct?
that's right.
And so that makes in each one an odd number.
That's right.
And
Correct.
so then the
Yeah,
operator
that's what it
is
is.
only odd.
Sure, yes. Other questions? And another way you can say it is, you can draw any arbitrary line and then sort of stack that on top of, the difference graph between any two configurations gives you a loop. So loop equations. Okay, good. So, so that's sort of the punchline for that model. Now, using this intuition, let me make a general definition, and this will bring us to this long-awaited subject of categories. So let me make a definition, and it's going to be again in the setting of this kind of geometry that I've been considering. So what I'm going to, let's see, the notation here is kind of awkward. Yeah. So let me consider some subregion, which I'll call R. Okay, and I want to understand excitation in this subregion R. Okay, so I want to understand. So first of all, I have my ground state psi, which is the ground state. But now I want to have a notion of, let me actually call that psi GS to emphasize the ground state. Okay. Now I want to have a notion of an excitation that is localized to the region R. Okay. So that's going to include, these kinds of excitations that I made here. So basically, what I'm doing right now is kind of formalizing this example into a general definition. So, so I'll say that. Some other state psi, not the ground state, but some other state psi, is an excitation that's localized in R if it looks like the same, if it looks the same as the ground state away from R, and in particular just on disk-like regions. So in other words, if whenever I have a disk-like region that's somewhere away from R, the reduced density matrices on this disk-like region of coming from psi. So rho is the reduced density matrix coming from psi. Is equal to the ground state reduced density matrix in region B, up to corrections which go like e to the minus distance between the region R and the matrix B where you measure correlations. Okay. So that, because I'm only allowing disk-like regions, that allows excitations of the above form. So like a string endpoint would be a localized excitation. Okay. So that's the notion of a localized excitation. Now, somehow I want to define anyons to be localized excitations, but there's something else I have to do, which is I have to, if I just define, anyons this way, then this contains too many excitations. I sort of have to quotient out by something. There's this definition of a localized excitations doesn't just contain anyons; it contains all excitations. Like any excitation that you can make that has some has some energy or something that looks like it's not the ground state in this region R. Is going to be an excitation localized at R. So I have to introduce some kind of a quotient. So this is sort of a typical thing that occurs in topology, and sort of taking a quotient. But the definition is that I have to introduce is that of a truly local excitation. So psi is truly local not just localized, but truly local excitation. If I can write it as some operator x localized in region R, just acting on the spins in region R, flipping some spins or doing something in region R, acting on the ground state. Okay. So certainly all excitations which are truly local, according to this definition, are localized, right? Because I only mess with the spins in R. I hit the ground state with some operators which flip spins on R. I haven't messed up anything far away from R, so certainly the reduced density which is far away from R, they're all the same. But on the other hand, the reverse direction is not true. So if I have an excitation that's localized in R according to this definition, you might not be able to make it with a truly local operator. And this example in the Torah code of a string endpoint excitation is precisely an example of an excitation that's localized but not truly local, because any local operators acting in the vicinity of where I make my perturbation delta H1 will, at best create an even number of string endpoints. There's no way you can create an odd number of string endpoints. Nucleate small string segments, they always have 2 endpoints each, so you always make an even number. Now, in general, what you can do is you can define, you can try to see what the quotient is. What is the set of all localized excitations modulo truly local excitations? Okay, you can try to define that. Yeah.
Does XR need to be unitary? The
No.
operator XR?
I don't think so.
If it's not unitary,
I get-
is it obvious that the root E is the same?
Oh. I guess if it's not unitary, you have to normalize. Obviously. Yeah, maybe you want it to be unitary. Yeah, let me just say unitary specifically. Yeah, you want to think of it as some physical process. Okay, so right, so you can define this quotient now. Sort of, this isn't really precisely defined. There is a precise, or at least a formal, or there's a formal definition of what this quotient means. But I'm only sort of going to say it roughly. So you want to define the set of all localized excitations modulo the set of truly local excitations. Okay. Yeah.
I must have blinked,
Uh-huh.
but the string was, the end of the string belongs to which either?
This one, but not this one.
The local one.
Yeah.
And that's the symmetries of region D, row.
Yeah. So the string-like excitation satisfies this property
Uh-huh.
because even though there's a string endpoint, so R is where the string endpoint starts. Even though there's a string, there's an endpoint of a string coming out here, the fact that there's a string emanating from here cannot be detected on disks. You need an entire so it does satisfy this, but it doesn't satisfy this. So in general, this quotient turns out, if you properly define it, this quotient turns out to be a finite set, and this is the set of anyons. What you call a set of anyons. Okay. And so that's already an invariant of a phase, like the cardinality of the set, like how many different anyons you have. That's already a signature of a topological phase, right? If I have 2 different gap phases, and they have, well, this is also just because there's different terminologies for it. This is also, people call this a set of topological superselection sectors. Selection sectors. I mean, it's just terminology for what this is. But so the point is that this just like the number of different anyons is already a signature of the phase. So if I have two different topological phases for which this set of anyons has different cardinality, different numbers, then I know that these are two different phases, right? Because this is a quantized invariant. It's only integer valued. So there's definitely no continuous way to deform one topological phase to another if they have different numbers of anyons. So at some point, the number of anyons would have to change discontinuously, and that's not a smooth process. There'd have to be some kind of a phase transition happening at that point. So it's already this thing as a set, the cardinality of the set, how many objects it has, that's already a signature of the topological phase. But it turns out that this isn't just a set. This there's a lot more structure associated to this set A. Okay, a priori it's just a set, but in general it's something that mathematicians call a category. So basically a category is a set together with a whole bunch of extra structure, and this extra structure can be physically motivated. Like it comes from certain physical constructions. So that's what I'm going to describe for the remainder of the lecture. So the extra structure that you can get for this set A turns it into something called a unitary modular tensor category. Okay. So let me sort of motivate what a category is with an example.
Can you motivate each of those words?
What's that?
Little phrase.
What?
Can you motivate each of the words? Unitary, modular.
Yeah,
phase,
yeah.
or category?
Yeah, so I mean that's what I'm going to spend the rest of the talk on, sort of each of those four words, starting with the word category. Right. So what is a category? So the rhetorical code example is nice because it's sort of the first illustration of how you can have a topological phase, but somehow it doesn't really capture the richness of what can possibly happen in this model of anyons, and it doesn't really motivate why you need to introduce something called a category. I mean, like in this toric code example, the set of anyons is actually pretty simple. So like in addition to this string endpoint being a possible anyon, it turns out that there's basically one other non-trivial kind of anyon. Just in the same way that a string endpoint is a violation of the vertex term, you can introduce a violation of the plaquette term. Okay, so there's sort of a dual excitation which corresponds to setting b sub p equal to -1 rather than +1, and that introduces sort of a dual excitation that's dual to a string endpoint. So the set of all excitations, you could basically, it's a very simple set. It's just a trivial excitation, string endpoint excitation, this dual excitation, and their combined product, and they actually form a group, Z2 cross Z2. There's one of the Z2s comes from the string endpoint because if you fuse two string endpoints together, you can get rid of them by joining them into a closed line. But that's a group. Okay, so somehow. That doesn't. Why do you need to introduce something fancy like a category when you can already understand this with a group? It seems like everything forms a group, but that's not true. That's only because the toric code is a very simple example, and it turns out that there's more general theories where the excitations don't form a group in any natural way, and that's why you need to introduce this notion of categories. Okay. Sorry, is there a question? Yeah. Well, there's lots. Basically, think of them as spin flip excitations. So like.
Spin flips always come in pairs. Does that make you want these string operators?
So a spin flip excitation. So, the spins live on links. So spin flip excitation is gonna, create a very short string, a single, a string of length 1 lattice spacing, and it's gonna have 2 endpoints. So any spin flip excitation is gonna sort of make a pair of endpoints, or destroy a pair of endpoints, or destroy one endpoint and make one.
Think of those as the truly local ones.
I'm thinking of those as true.
Localized ones are advanced kind of
The localized ones are, you're going to make an operator that explicitly makes one. So the localized ones are, consider an operator that's product over all links L in some path times sigma Z L. Okay, so I have some path that's very long. Okay. And I just multiply over all the links that are contained in this path. I multiply sigma Z. Okay? So then that makes a very long string if you think of it as sigma X configuration eigenstates. But naively you might think, oh, that just creates a very, it doesn't create a point-like excitation. I've sort of messed, I've acted everywhere along the string, so that it's going to have some finite energy density everywhere. But in fact, this operator commutes with the Hamiltonian in the bulk of the string, right? Because in the bulk of the string, it certainly commutes with the plaquette terms. Those are made out of sigma z's. But it also commutes with the vertex terms because, it doesn't make vertex excitations in the bulk. It creates a single string. So in fact, the string operator only leaves energy here and here. It actually only modifies the density matrices on disk-like regions here, here, and here. So this kind of string-like operator, which commutes with the Hamiltonian in the bulk of the string, is what creates the localized but not fully local excitations. Yeah.
The question is, what is the sharp distinction between the localized excitation and truly local? Because, for example, we need to define what is very long path.
Yeah.
In this sense, we can say that very long path is, say, 5 bonds. For example, we can say that it is also 10 bonds or 3 bonds, but 1 bond is already truly local.
Yeah, so I want it to be much longer than the correlation.
Okay. It's basically the correlation.
Yeah. So the nice thing about the toric code model is the correlation length is 0 in the toric code model. All correlation functions just drop off after 1 lattice spacing, so everything's sort of simple in the toric code model, but yeah, in general gap models, there's a correlation length, and that's the fundamental of it. So when I say long is with the correlation.
So that quotient set is independent of R, as far as R is larger than the correlation?
Yeah, absolutely. That's sort of the nice thing about topological. Okay, other questions? Okay, so right, so I already said that even though in the toric code this set A forms a group, and the group is a sort of relatively simple mathematical object, it's actually an abelian group. In general, that turns out not to be the case. In general, you can have really weird models where the things, the set of anyons doesn't really form a group. It forms a more complicated structure, and that more complicated structure is captured in this idea of a fusion category. So, one example actually, which is kind of useful to further motivate things, is sort of a minimal generalization of this toric code model. So the toric code model, you can think of it, if you know lattice gauge theory, it's a Z2 lattice gauge theory. It's a lattice gauge theory based on the group Z2. But one thing you can do is to generalize this, think about a non-abelian lattice gauge theory. So where G is some non-abelian group. Okay, so it's a gauge theory based on a non-abelian gauge group G. So in order to have a deconfined phase G in 2 dimensions, G should really be a finite group. So you could take G to be some non-abelian finite group, like a dihedral group on some number of elements, or just whatever your favorite non-abelian group is, S3 or something like that. For the purposes of just intuition, you can really kind of think of, I'm running into pedagogical difficulty here just because I don't want to start like writing down complicated finite non-abelian groups. And this isn't, of course, in group theory. So just in the back of your head, you can just kind of think about G being SO3. It's a non-abelian group that everybody knows. It's the group of rotations 3 dimensions. Now, certainly an SO3 gauge theory in 2 dimensions will not have a confined phase. So what I'm actually saying really should be applicable to finite groups G that are non-abelian. But just as a way of if you can't think of an example of a finite non-abelian group, just think of SO3. All the intuition goes through fine. So in a non-abelian lattice gauge theory, based on a non-abelian finite non-abelian group, just like in the toric code, you can also get a model of anyons built in this way. But now there's sort of an additional complication, or an additional feature, I guess you can call it, which is that some of these anyons, which correspond to the charges in this gauge theory, just like the string endpoint was a charge, was sort of a source of Z2 electric flux. In the non-abelian lattice gauge theory, you're going to have some charges which are sources of this non-abelian flux, and in general, charges in a gauge theory correspond to representations of G. Okay, and if you have a non-abelian, or if I want to think of sort of simple objects, they're going to be irreducible representations of G. Representations of G. Okay. And if I have a non-abelian group, I have irreducible representations which aren't just one-dimensional. So in the toric code, that's a Z2 gauge theory. Z2 is an abelian group. The representations are all one-dimensional, and so I don't see this feature that only comes up when I consider non-abelian groups. When I consider non-abelian groups and the gauge theories that are built on them, I have irreducible representations that start appearing which have dimension greater than 1. So if you're thinking about SO3 intuition, you have like the spin 0, spin 1/2, spin 1, etc. And all these higher spin representations have degeneracies in them. Okay. Similarly, for non-abelian groups, you have the same thing. You have some representations which have dimension greater than 1. And that's a complication. That's a feature that you don't see in the toric code model. But the point is that it does appear here. And so the intuition is that the excitations here in this model, like the charge excitations, sort of have additional degeneracies, additional Hilbert spaces that are attached to them. Okay, so if I can think about a charge excitation, label it by Q, there's a Hilbert space that's sort of attached to it, finite dimensional Hilbert space HQ, degenerate Hilbert space, which is sort of the representation in which it sits. And that could have some degeneracy associated to it. Okay. And in general, if you sort of want to describe the full structure of excitations in this non-abelian lattice gauge theory, you have to think about not just the charges, but also the flux excitations. And then you can have really interesting things happen where, if you have a charge excitation here and a flux excitation here, so flux excitations are labeled by conjugacy classes of group elements, but roughly you think of them as group elements. And what can happen is, you can take this charge, let's say, around this flux excitation. Okay, so you move a charge around a flux, and just like in the U1 case, where if you move a charge around a flux, you pick up an Aronoff bone phase. In the non-abelian lattice gauge theory, you pick up something sort of more complicated, which is actually a linear transformation on this Hilbert space, right? Because G, basically what happens is the Hilbert space that's associated to a charge is some representation of the group, and roughly what happens is when you go around, there's some linear transformation. So G acts in the Hilbert space and does something.
So this would happen in like SU to level 2 or Baktian. Is that right?
Well, so right now this isn't even getting that complicated because these are all I'm thinking about basically all the quantum dimensions here are integers. So in the discrete lattice gauge theory, all the quantum dimensions are integers, and I'm sort of saying that's already complicated. But then the next thing I was going to say is what you mentioned, which is that.
Then at least I feel like there's some physical system associated
Right. Well, I mean, for this, you can write down exactly solved models. Just like you can write down a toric code, you can write down exactly solved models from ideal manifestation. So there's physical systems as well. But so the point is that this is sort of a step up in complication above the toric code, right? So you don't just have a set of excitations, but you have additional data. You have the data of Hilbert spaces, vector spaces that are being attached to these excitations. Okay, you have additional you have additional data. Okay, right. So I was going to say something. I forgot what I was going to say. Okay. So right. So there's a very simple. So what's the structure that appears when you consider this example? Well, I said that I get these Hilbert spaces that are attached, these finite dimensional Hilbert spaces that are attached to excitations, and they all form representations of G. Okay, so it turns out that the set of all representations of G, this is sort of a non-trivial example of a category. Okay, so this sort of has two things. It has objects, which are representations of G, and it has something that mathematicians call morphisms, which are linear maps. Actually, in this case, they're also unitary. Everything's unitary, so unitary linear maps between representations. Okay, so right. So you have representations of G, which are attached to at least your charge excitations. There's actually also representations that are attached to your flux excitations. It's just that they're not representations of G, but rather representations of some subgroups of G, which are invariant under whatever flux you're looking at. But roughly the idea is that this is what you have. You have Hilbert spaces, which are representations of G, which are your objects, and then sort of operations that you can do, physical operations that you can do, are somehow represented by unitary linear maps, like a braiding operation at the level of sort of what it does to the objects, what it does to the low energy states that are encoded in these Hilbert spaces. They're all acting as some linear transformations. Okay, so this turns out to be the simplest example of a category. This is maybe not the simplest example. The simplest example is just like the set of all Hilbert spaces and linear maps without even having a group. That turns out to be a category. But here, I have a group. My objects are not just any old Hilbert spaces, but they're Hilbert spaces which form representations of G, and the morphisms are unitary linear maps. Oh yes, so I'm sort of conflating two different things. Let me see some morphisms. So for rep G, the objects are representations of G, and these are unitary maps of representations. So there's some compatibility conditions with the group structure. I don't want to really go into this too much, just because I want to say that even this, this idea of just assigning Hilbert spaces, to sort of capture the various degeneracies that are associated with various quasi-particles, is not enough mathematical structure sort of to capture the full weirdness of a topological phase. So you can have examples of topological phases where you still have degeneracies that are associated with different excitations, different localized but not fully local excitations, different anyons. But those degeneracies cannot be accounted for by assigning local Hilbert spaces, finite dimensional Hilbert spaces to each point. Somehow, there are very famous examples of systems where where instead of having some integer number of degenerate states associated to each point, you actually get some irrational number, like √2 states associated to each point. Now, of course, that doesn't make any sense for a single excitations to have √2 states. What this really is a statement about how many what is the degeneracy corresponding to some finite collection of excitations. But the point is that that can't really be captured by associating Hilbert spaces or representations of some group or anything like that to points. You really need this more general framework of a category. And so, the intuition that I have, the intuition that I like to think about is basically that just like any representation can be, well, the intuition that I like to have is that the intuition that I like to have is I like to think of a general category as some kind of a generalization of this representation category. So just like any, just like you have in the representation category, the fundamental things are the irreducible representations of some group, and you can build everything out of that. In a general category, that's appropriate for this stuff. You still have some fundamental objects which are analogs of irreducible representations, but they're not, they're not actual representations. They don't have actual Hilbert spaces associated to them. They're just some kind of, for lack of a better term, objects. This is what mathematicians call them, objects. And all the structure that sort of comes naturally to having representations, like for instance, if I have two quasi-particles in this non-ideal lattice H-theory example, and they have two different Hilbert spaces of degenerate states associated to them, then if I merge these two, if I just look, I don't even have to merge, I can just sort of look at it from far away, the collection of those two quasi-particles, there's going to be, if I have two states on one, I have two states on the other, I'm going to have four states. I just take the tensor product of Hilbert spaces. There's a very natural tensor product operation. In the general case, I don't have that, so I'm going to have to sort of build that up from scratch, right? So that pertains to this word tensor. Because physically, when I have excitations in a topological phase, I can still sort of merge them, or at least look at them from far away. So there should be some notion of tensoring, of putting things together. But what the implications of that are, what are the consistency conditions that this tensor has to satisfy, that's something that you have to sort of build up from scratch, because you don't have this pre-built notion of a Hilbert space associated to each excitation. Okay, so that's what what time am I ending?
2 minutes.
2 minutes, okay, great.
2 more words.
Two more words. Fusion and braiding.
1 minute.
1 minute. Okay, let's see, what can I do in 2 minutes? I can draw some diagrams, okay, that's fine. I know what honestly, in 2 minutes I can't do that much, so let me leave you with this. So there's a paper by Alexei Gitayev, and the paper is long, but specifically Appendix E. No, I'm serious. This is a very well-written appendix, which could be a paper on its own, which basically derives all the properties, all these things that I said I would talk about, but I didn't get time to talk about. How does the word, how does unitarity come up? How does modular come up? What does that mean? How does tensor come up? He really, so this is by Alexei Gitayev. He really starts with some basic physical assumptions, and you don't actually have to read the rest of the paper. You can just really start at the beginning of Appendix E. Starts with some very basic physical assumptions and extracts this structure of a category, sort of step by step, all the pieces of it in this Appendix E, and sort of shows how once you have all that structure, it really, it's a very sort of discrete, rigid structure where there's not much room for variation. There's basically no free continuous parameters in the unitary modular tensor category. And so this unitary modular tensor category, it's sort of a discrete thing that itself, as a mathematical structure, you can think of it as a quantized invariant that's associated to a phase. So yeah, I guess what I'll leave you with is take a look at Appendix C. It's great, and there's no typos, which is amazing. Okay, thank you.